All right. And let me share my screen again. Okay. So it will be like 10 minutes recording. Okay. So let's see here which one of these you think is true. When percent hydrophilicity is low, a protein forms a better emulsion when water is the dispersing phase. When percent hydrophilicity is low, a protein forms a better emulsion when oil is the dispersing phase. When percent hydrophilicity is high, a protein forms a better emulsion when water is the dispersing phase. So emulsion, what emulsion, it can be oil and water. And if it's oil and water, then water is your dispersing phase. Or it can be water and oil, then oil will be the dispersing phase. So basically butter is water and oil. Oil or fat is your dispersing phase. All right, let's see. I see lots of answers here. Yeah, I see a lot of E's, which is correct. Yes. So when you have surface hydrophobicity is higher, then it would be good if your dispersing phase is oil. When surface hydrophilicity is higher, then it would be good when the water is your main dispersing phase. So it's basically B and C.
Pam, I had a question. Does percent hydrophilicity always mean surface hydrophilicity, or are they different?
No, there is total hydrophobicity. You have assays where you can determine total hydrophobicity, but then there is specific assays for surface hydrophobicity, where you determine the hydrophobicity on the surface.
And in this question, we were speaking about surface hydrophilicity.
Yes, I should have indicated that, yes. So globular proteins can form thick films at the oil-water interface, tend to form smaller, thinner adsorbed layer, can impart extended emulsion stability. So what happens at the interface of the emulsion, we're going to talk about that when we talk about emulsions quite a bit, is that the protein unfolds. So it moves to the interface because you have two phases. You shake them, and then you have the aqueous, and then you have um, the lipid phase. If you don't have any emulsifier, they're going to separate due to surface tension. But if you have an emulsifier, it's going to go to that surface and unfolds and reorient itself, its hydrophobic components to the oil phase or the lipid phase, and the hydrophilic components to the liquid phase. So there is unfolding that happens. And there are several proteins, if the protein is your emulsifier, several proteins will start forming a film around your oil, right? So the more proteins make it to the surface, the more proteins you have on that surface around the oil, the thicker is the film. So the thicker is the film, the more stable is your emulsion. That means the more stable that the oil droplets won't fluctuate and won't coalesce and open to be one big oil droplet. So the thicker the film around the oil droplet, the more stable that emulsion is going to be. So what would make the film thicker is the more proteins that make it to that surface. So globular proteins are smaller proteins, so more of them can make it to the surface. If you have an open structure protein, large open structure protein will take a lot of space, and then it will form a thin layer around your oil droplet. However, globular proteins, they would unfold partially, but they're still structurally more compact. So more proteins can make it to the surface and form that film, and the film becomes a thicker film around the oil droplet. So basically globular proteins can form thicker films and can impart extended emulsion stability. So A and C in this case. So the functional property. So this is a definition of the functional property. So a physical-chemical property which affects processing and behavior of food systems. And we usually judge it by quality attributes of the final products. I mean, what's the texture? Mostly it is the texture, the physical characteristics of the final product. So the functionality is influenced by so many different factors, including complex interactions between the different components and the structure. So the amino acid composition, basically, the structure of the protein at the end, the physical chemical properties, including net charge, the surface properties, hydrophobicity, hydrophilicity on the surface, reactive groups, presence of sulfhydryl groups, for example, presence of ionizable groups, and the presence of other components. So other components, how much water you have, what you have, lipid, do you have carbohydrate, etc. And the nature of the environment in this case could be pH and ionic strength. So all of these components impact functional properties. So they impact the protein structure, and therefore they impact the protein functionality or functional property. So this is a table that kind of summarizes general property and then the specific function term. So for example, if we talk about hydration, what do we mean by hydration? So protein-water interaction. So solubility is one functionality that is related to hydration. Wettability, when you put the powder and you put it in water, how easily it gets dispersed in water and gets soluble in water. Swelling, viscosity, water holding capacity, anything that has to do with interaction with water has a hydration property. Surface property, anything that has to do with surface interactions, such as an emulsion formation or foam formation. So where we rely mostly on the surface properties of the protein and their interaction with the different phases. Structural, textural. So when we talk about viscoelasticity, for example, that is a textural rheological property. Aggregation, gelation, that is a texture that changed. The protein in solution became a gel. So that's a structural, textural, rheological property. So this is FYI table that kind of introduces different functional terms and how they relate to the general property. This is also another FYI table that talks about a function. So for example, we'll look at solubility. What's the mechanism of protein solubility? It's hydrophilicity, how much it's interacting with water via hydrophilic interactions. An application is a beverage, and most common protein used in this application is whey protein. So you can look at different functions, the mechanism of each function, the food example, and most common protein type. Of course, this is an old table because it doesn't show any of the new plant proteins that are emerging. But this is a table that mostly features the common traditional proteins: whey, casein, gelatin, egg, meat, and cereal protein. Okay, I think I'm going to stop here with those general information because next time I'm going to go into specifics of each of these functional properties. So it'd be a good stopping point for today. And you'll have two recordings. One is short, very short compared to the other one. All right, so I'm going to stop sharing. Any questions before we leave? Okay, good. We'll see you later. Bye.